Section 4.3, permutations when all objects are distinguishable. So that means all objects are different. So here's a permutation. How many three-letter permutations or arrangements can you make with these letters? So there's 4 letters, they're each different. So how many different ways can you arrange this? What we're going to do is we're going to say, okay, we have 3 spots. Oops. We have 3 spots. In the first choice, we have 4, 1, 2, 3, 4. Then we've used one of the letters, so we have 3 choices and 2 choices. So we have 4, and this is fundamental counting principle, because how many ways can you choose this, and this, and this? 4 times 3 is 12, times 2 is 24. There's 24 ways that you could arrange that in 3 letters. And that seems a little incredible, right? But when you actually start start looking at them, you can see that it would be easy to start to get 24. I already have 4 right there, and then plus there's all the other ways that we could arrange it. So there is 24 ways. Okay, next slide. Here we have Chloe, and her school is holding elections for 5 positions on next year's student council: president, vice president, treasurer, secretary, and social convener. And these are all the people who are running. How can she determine the number of ways she can fill out her ballot if she considers only voting for some of them? So how many ways can she fill out the ballot if she votes for all 5? Well, so in this one, there's 5 people. She has 5 choices for president, then 4, then 3, then 2, then 1. So it would be 5 factorial. And it would just take using your calculator to figure that out. Okay, using the fundamental counting principle, using the fundamental counting principle to write the number of ways she could find her ballot for each of the following number of positions. Leave your answers in factored form. She votes only for president, so she has 5 choices for president, 4 choices for vice president, 3 and 2, so these are all multiplied. She votes only for the president, the vice president, and the treasurer, so she has 5 choices since there's 5 people, and there'd be 4, 3, okay, only for president and vice president, 5 times 4, and for the president, well, she has 5 choices, so she can choose any one of these 5 people. Okay, let's move on. Natalie claims that the expression 5 factorial divided by 1 factorial represents the number of ways she can fill out the ballot to vote only for the president, vice president, treasurer, and secretary. Do you agree? Okay, so she has 5 for the president, 4 for the vice president, 3 for the treasurer, 2 for the secretary, and then divided by 1 factorial. So let's look at that. Well, this is equal to that. We cross off the 1s. Oops. 5 factorial, we cross off the 1s. So that is just 5 times 4 times 3 times 2. And we had said that it was going to be 5 times 4 times 3 times 2. So those are equivalent. Interesting. Okay, by the fundamental counting principle, this product represents the number of ways she can fill out the ballot. Next up, D. Use Natalie's idea to write the expression involving the quotient of 2 factorials for each of the other choices. So she votes only for the president. We said that was 5 times 4 times 3. Well, we could rewrite that as 5 factorial divided by 2 factorial, because it's like we go 5, 4, 3, 2, 1, but we're not, the 2, 1 has been canceled out. Okay, now this is only for the vice president's 5 times 4. Well, we could say that was 5 factorial divided by 3 factorial. Okay, and this last one we could say, well, that's 5 factorial divided by 4 factorial. And that's the same answers they got. Okay, last page. How does the number in each expression in part D relate to the number of positions in the ballot and the number of positions she votes for? 5 to 2. Well, here she had 3 choices. So this is kind of like 5 factorial, oops, 5 minus 3 factorial, because there was 3 things she was voting for. And this is kind of like 5 factorial over 5 minus 2 factorial, right? Because she was voting for 2. And this would be like 5 factorial divided by 5 minus 1 factorial, because she's voting for 1 thing. So this is the whole idea of this section. Suppose that there are n positions on the student council and she votes for r of them, where r is less than or equal to n. Write an expression that would represent. So she would go n factorial over n minus r factorial. That's the whole idea. So it's saying you have, in this case, 5, and it's 5 minus the number of positions you're trying to fill that you divide by. That's kind of what we did here too. We had 4 factorial divided by 4 minus, we only wanted 3 of them. So 4 minus 3 is like 1 factorial. So it was like 4 factorial over 1 factorial. That's the whole entire idea of this section. Okay, last page. This is what I just want to look at. NPr is the notation commonly used to represent the number of permutations that can be made from a set of n objects. So I have 5 different objects, and I only want 3 of them. And it's always that r is greater than or equal to 0, and n is greater than r. When all objects are used in the arrangement, n and r are equal, so the notation npn is used. Okay, so this is the way we state this, NPr. And let's give this a try here. And NPr is simply equal to n factorial over n minus r factorial. Okay, that's what NPr is equal to. That's an n there. Okay, so Matt has downloaded 10 songs for an online music store. He wants to create a playlist using 6 of them in any order. How many different can he make? So this is really 10p6, and that's equal to 10 factorial over 10 minus 6 factorial. Okay, and what that simplifies to be, that's really where my arrow should be, sorry, or where my brackets rather, is this is 10 times 9 times 8 times 7 times 6 times 5, keep going, divided by 10 minus 4, oh, I should keep going, 4, 3, 2, 1, just to be a good mathematician. 10 minus 6 is 4, so it's 4 factorial, which is 4 times 3 times 2 times 1. So the 1's cancel, the 2's, the 3, the 4's, and we're just left with 10, 9, 8, 7, 6, 5. And they've already done the work here, so I'm going to show you. 10, 9, 8, 7, 6, 5 is equal to this. Okay? So that's how to do it. Another way we could have done it is we could have said, well, the first song, there's 10 choices, 9, 8, 7, 6. That's the other way we could have done this question. Okay. I just want to talk a little bit, there's a couple questions I have you doing like this, where it says, state the values of n for which the expression is defined. So what that means is, we do know, I will tell you that 0 factorial is equal to 1. So the lowest number we can have represented by factorial is 0. So it's saying what value can n be? So this is greater than or equal to 0. So what we're going to go is n plus 3 is greater than or equal to 0. So n must be greater than or equal to negative 3. And all I did is I moved that over. I subtracted 3 from both sides. Because if you had anything less than that, if you had negative 4 plus 3 is negative 1, negative 1 factorial doesn't make sense. So that's what it's asking here. Okay, and B as well, it's saying, what are the values of n that make this make sense? So n has to be greater than 0 in the numerator, and it has to be greater than negative 2 in the denominator. Both expressions must be defined, so we have to go by that highest number. So n must be greater than or equal to 0. Because if it was less than that, if it was negative 2 on the top, it'd be fine on the bottom, but on the top we'd have negative 2 factorial, which doesn't make sense. So there are a couple questions like this that I have you do. Okay, I think I have one more I wanted to do. Tanya needs to create a password for social networking website that she is registered with. The password can use any digits from 0 to 9 and the letters of the alphabet, but the password is case sensitive, so she can use both lower and uppercase letters. A password must be at least 5 characters to a maximum of 6 characters, and each character must be used only once. How many different passwords are possible? Okay. So this involves cases. There's going to be 3 cases. We're going to look at 5 character, 6, and 7 character cases, and then we're going to add them up to get the total number of cases. So let's look at all the elements that we can use. We can have 0 to 9, so that's 10 different choices. And then we can also have 26 letters, but they can be both lowercase and uppercase. So in total, we have 26 and 26 is 40, 52 plus 10. We can have 62 different digits. So it's like we have the fifth case, we have 62, but we only want 5 of them. This case, we have 62P6 and 62P7. Those are the cases. We're going to add those up. Okay, and now is when we're going to go look in our calculator. In your calculator, you should have a button. Sometimes it's called probability. Sometimes there is actually a little button on your calculator that is NPr, and usually you enter N, then R. And that's the way we're going to do this one, just because it'll be easier to do it in your calculator. If not, you could go 62 factorial divided by 62 minus 5 is going to be 57 factorial. You could do that as well. But I'm going to get you guys to try and spend some time looking on your calculator for that NPR button, okay? And then you're going to get 3 values and add them together, and your total answer should be 6523690780000. So that's huge. So in general, when it's like 5p3, that's really simple to do 5 factorial over 5 minus 3, which is 2 factorial. That's easy to see, okay? But when you get like numbers like 62, that's when you're going to use your calculator, okay? So if you need help finding that calculator button, don't be afraid to send me an email or come talk to me. The number of permutations from a set of n different objects where r of them are used can be calculated using this formula. NPr is equal to n factorial over n minus r factorial. So, and they give an example here. When n objects are used, n is equal to r, and the arrangement is represented by npn, or n factorial. And that's like what we did in section 4.2. The number of permutations can be created from a set of n objects using r objects in each arrangement, where repetition is allowed, is n less than or equal, r is less than or equal to n is nr. For example, the number of 4-character passwords using only 26 lowercase letters where letters can repeat. So if they say can repeat, then it's just 26 to the 4, n to the r. So this is if we can repeat, okay? If order matters, then the problem involves permutations. To determine all permutations, use the formula for NPN or NPR, depending on whether all or some of the objects are used in each arrangement. Both of these formulas are based on the fundamental, that AND word, counting principle. By definition, 0 factorial is equal to 1. As a result, any algebraic expression that involves factorials is defined as long as the expression is greater than or equal to 0. So remember I said there'll be a couple questions like this. If counting a problem has more than one condition that must be met, consider each case that each condition creates first as you develop your solution, and then add them. Okay?